As Angie said, my name's Colin Pace, and I worked at IBM at Hersley for over 40 years. My job there was covering Kix, Build. I spent over 25 years at in MQ, and one of my jobs there was performance. So I've always had a performance interest since then. Since I've retired, I run ZOS on my laptop, and I get into all the interesting corners of ZOS that I never had time for before. Um, Currently, I'm looking at Zoe, and when I run Zoe on my baby laptop running ZOS, it takes about 25 minutes to start up with all the address spaces. I believe if you run it on a proper box, it takes minutes. So that's why I thought, oh, this looks an interesting area, trying to find out why Java is slow. I mean, it's not just Zoe, it's things like ZOSMF is slow. Everything running Java tends to be slow running this sort of second level ZOS. And one of the areas I found for improvement is the use of Java shared classes cache. Now, with all the work I've done on this, it takes about 20 minutes. So I'm going to spend the second half of the presentation covering interesting performance things. Some things are really obvious once you see them. Also, one or two things made my head sort of think, wow, what is this doing? So I'll cover those. So I'll have a short break in the middle to answer any questions you have on the shared classes. And so without further delay, I'll get on with what I'm doing. Going back to when I first joined IBM, I worked on VSE. And in order to open a file, you had to load a module $B open into the transient error. You'd run it, you'd execute it, then you release the module. To read a file, you had to load a module $B read into this transient area, execute it, and release it. So you spent most of your time doing file I/O, opening and closing and loading these modules into memory. So this is actually very expensive. With ZOS, we have the link back area. So all the modules for opening and closing data sets are now stored up in memory. It's like a 12 instruction path length to get to these modules in common storage. Java shared class is just like the LPA, except for Java. So it actually stores things in common memory and makes startup much faster. To me, it cuts down, it halves my response time when starting Java. It's that sort of a benefit you get. So let's have a quick look at a Rex program. So I have a very simple Rex program at the top, and it's basically this is a comment, it's an if statement, a do, and a return and blah. What Rex does, it does a lazy parse. It only reads what it needs to read, which is basically the start and the stuff. It does not need to parse the last comment at the end because it never gets there. As parsing it, it basically builds up a tree, says, this is an if statement. And there's an if clause, which happens to be x equals 1. Then there will be a then clause and an else clause. And it builds up an in-memory tree of the actual program. I know that once one of the IBM products running a web server calls a Rex exec for every call coming into the web server. And this exec was over 5,000 lines long, of which 4,000 were comments. So just by deleting the comments, the processing went twice as fast. With Rex, it's always been a bit slow, but they have what's called compiled Rex, which basically takes this program, gets rid of all the comments, and saves the parsed statements. That's the if clause, the then clause, and else clause in the file. So now when you run a compiled Rex program, it's much faster than an ordinary program. You might still need to read it from disk, but the file will be much smaller. So generally with compiled Rex, it's much faster. I would hope that lots of people these days use Rex and they can understand this. This should be old knowledge for most people. Looking at a Java program, you can actually run in Java and say, here's my prog.java, and Java will execute it. But what people tend to do these days is actually compile it, and it converts it from the source we see at the top into the byte codes on the bottom. And so we see such things, and instruction 0 says, put the constant 2 onto the stack. It then says, invoke a routine called nested class. And on the right, we see the picture. All it basically does is puts the value 6 on the stack and returns. Instruction 4 says, add them. 5 says, store it, and then says, ready for the next instruction, load it back into memory before doing the printout. So this is the Java bytecode which is used internally. Java has classes, so we can see there's two classes there. There's the main class and there's the nested class. Right, with the bytecodes, Java takes these and interprets it. So you could think of a program reading those bytecodes and actually jumping off to a subroutine called constant2. With the Java shared classes, it does some what they call ahead of time compiles. What I tend to think of is putting these subroutines in line with the mainline code. Java also has what's called just-in-time compilation, and that basically uses compiler technology to optimize the code. And for example, if you find that you're going around a loop 10,000 or 10 million times, Java will say, I can optimize this loop by using the following instructions, or these constants don't vary, so I'll move them out the loop and have a smaller loop. And for example, of hotspot analysis might be to say, actually, in the previous code, we stored the variable, then we immediately we unload it again. So actually, those two are redundant. So that can actually be optimized by not doing that. So the just-in-time compiler is used. You'll find you start your Java program, and over time it gets faster and faster because more and more code is JITted, and it all runs faster. The way it works is if when you're going through your Java code, it might say, actually, I've been through this piece of code here 1,000 times. I will now put a request on a JIT thread saying, please optimize this class. So JIT goes away, and over time it says, okay, I've got this instruction, I'll optimize it, and I'll replace the instructions in memory with the JITty code. Right, so how does Java start up? So first of all, there's some C code which basically loads some programs which allow the Java stuff to be loaded. And it loads what's called the bootstrap code. And this is the code that Java needs itself to actually execute Java code. And eventually it says, okay, I'll now start the Java interpreter. So now it gets to you, says, your program's called myjava.class. I will go and load it. And it says, is this already in memory? No, it's not. So it goes off to disk and loads in from disk, parses it just like we saw with the Rex, and generates the ahead of times compilation in line and saves that in memory. If it did exist, it can jump straight into reusing it. So what the Java shared classes cache does, instead of saving this data in the JVM's region, it uses some MVS shared storage itself, and it saves it across JVM iterations. So if you're using the shared classes and shut down your JVM, next time it starts, the data is already in memory. So you do not have to go through this low class, parse the data, etc. And that's the benefits of the Java shared cache. It'll still do optimizing the code, and as JIT optimizes the code, it'll update the shared memory. And so over time, the shared memory element gets updated. Now, a bit of technical stuff. There's two caches. You can use non-persistent and you can use persistent. I'll mention persistent parsing in a couple of minutes. Java allocates a shared memory segment and gives it a name. And it stores the stuff in, hence it's called the shared classes cache, or SCC. So you'll see lots of references to SCC in the documentation. When you restart Java, it can exploit this shared cache. And for example, if you have multiple address spaces running Java, they can all exploit the same shared cache. You can say, please save a copy of this shared memory to disk. And you can also say, please read from this file and create an in-memory segment. So these are the basics of how it all works. And to give an example, in your first IPL of the day, you run your Java, your JVM, and first time it is slow because it's got to read all the classes from the file system into memory and parse it. If you now shut down and restart your Java, it'll be much faster because it's already being parsed and it can use a shared memory. If you start a second JVM instance, it can use the same cache. So in that case, this is faster. And at the end of the day, you can say snapshot to disk and save a copy for a future date, like after the IPL. So now on an IPL, I say restore the snapshot from disk. And now the first Java to start is much faster because it can exploit this shared class cache. And just as before, you can shut down and restart. So everything's fast if you can use this shared cache. A bit of technical detail. For most people, you can forget this, but it uses a file name as a semaphore. So if you've got multiple JVMs updating this cache, it uses a semaphore and linked off a file name to actually serialize access to it. This shared memory is just like a file. So for example, you've got ownership of it, you've got group owner, you've got user ID owner, you've got permissions and so on. And if you want to display things about the shared memory, you can use the OMVS IPCS command. This is not the dump formatting IPCS. This is the inter-process control something or other commands to display the status. How do you configure it? You specify a shared classes. You can say -x shared classes. And you pass in the cache directory, and this is where it stores the files. In this case, I use the directory /u/temp/zoec, and you have to give it a name. So, for example, you could have different JVMs, each with their own instance of the shared cache. In this case, I'm saying they all use the same version of Zoe GW. And I said, this is the access, the permissions that people can have. So the permissions of 777 means anybody for the user, the group, or any user can have access to it. This may depend on what you want to do. You might just want to say only the owning user ID can access this cache, but that is up to you as a user. How big? Look up the parameters. If you look on the file system, you can see the /u/temp zoec, which is the green stuff, is what you specified in your shared classes parameter. And Java creates a subdirectory called Java Shared Resources. Within this, there are at least 3 files. So we can see the first one, it's got the M21, and this is the level of Java. So I can see I was running with Java level 21 on the system. It's got the name Zoe GW, which is what I pass as parameter. And this file has 84 megabyte, and this is a hardened copy of the shared memory. It's also got a semaphore file called Zoe GW with the word semaphore in it, and the memory file. The default directory for storing files is /tmp, which I think is a terrible name, terrible place to put it, but there isn't a better place. The ls-i command gives you the inode number of the files. An inode number is basically a unique identifier for each file in the file system. And for example, my memory file has an inode of 803, which in hex is 0x323. Then if you display the show memory using the IPCS command, you can see that name is actually in the key. So every shared memory segment in MVS has a key. And Java 661 on the front, followed by the inode file and a number at the back. And you can see, for example, that the owner has read-write access to this file. The group has no access, and users have no access. The owner is the user ID ZWESVSUR, and the group is Zoe admin. And similarly with the semaphore file, the RA means the owner can read, but also alter the semaphore file. What caches are there? There's some commands you can use to display information about the shared classes and the cache. So first of all, there's a list all caches, and you give it the directory specified and the name. So in this case, it says, okay, in this cache, in the file /u/temp/zoec, there are 2 files. One is a non-persistent and the other is a snapshot. So I can see, oh yes, this is the Java 21 64-bit. These what I expect. So the snapshot is one I saved a copy onto disk, and the one above it is the in-memory currently in use. If you say print stats, you can get lots of information. So in this case, the cache size is 26 megabytes. Half of it is used. There's 11 megabytes free. There's 37 meg, is it, of classes? It doesn't quite make sense. So you can actually get a sizing of how much is actually in use and how much is being JITted. You can actually then say print all stats, and I suspect most people will not need to use this. I did because I kept trying to find out why things weren't being loaded. If you look at the box on the right, it says set X. This is a piece of Java code. And with a set, you can say, please give me the size of the set. So you might have a bit of code which says I equals the size of the set, and you say size bracket bracket. If on the shared in the printout, it will say there is a class, a Java class called Java Utility Set, which is what this is. It has a method called size, and it's a signature bracket bracket which says there are no parameters, and it returns an I. And here's some parameters, etc. You can also do a comparison for equals in two sets. So you have one set and say, is this the same as the next? If you look at the signature, you'll see it passes in a Java object and returns a Boolean. So from this, you can see all the methods that have been loaded into the shared classes cache and what the signatures are. And you'll see I get some size as well, I think. So this is a tremendous amount of detail. It's like 190,000 entries I had when I printed out one of these from Zoe. And that's the lowest level of detail. As I said, most people won't need to go into it, but if you're a Java developer, you might be interested to see what's actually going on inside. If you want to back up your cache, you say snapshot cache, and it saves it to a file in the directory, which I showed you earlier on. And the opposite is you can restore from the snapshot, and that says create a copy of the in-memory cache based on the disk image. Now, if there's an existing shared memory cache there, it will not restore it. So you run this from an empty system and it'll build the cache for you. Now, I had great problems trying to do things like backup and restore of the cache from my user ID Pace, which was different to that used by Zoe. So my recommendation is to use the same user ID for backing up and restore as you do when you run it. So what I actually done now is to change my Zoe startup to say, first step, restore the snapshot. But at the end of Zoe, as it shuts down, I put an extra step in, which basically says snapshot cache and save a copy. So that way it's automatic and I don't have to do anything to get it to be installed or to save it. There's also commands called reset and to destroy. So reset basically it says empty the cache, and destroy says, okay, delete it and remove the entries on disk as well. So that's a non-persistent cache. There's also a persistent cache. Now this, I think, only came in, I think, in Java 21 or 23. It's been available on the OpenJVM on distributed for many years. Instead of writing to shared memory, it writes to a memory mapped file. And as far as I can see, every time you update the memory mapped file, it does a file IO. So to me, this feels slower than using the pure in-memory copy. It may be that it's actually slower than the non-persistent cache, which explains why there's not much documentation on it. I also getting it working. I had problems. You have to change some of these ZSMF, the SMF limit parameters to say this user ID can allocate a big segment for a shared memory file. I blogged on this. If you search for things like this and for with the keyword Colin Pace, you should find the work I did on this area. Updating the cache. If you update the cache, so for example, you recompile your program and update the copy on disk, I'm not entirely sure what happens. I read one thing and that made sense. Read something else and it was different. So when you say find class, it will check to make sure the same path is used and the date timestamp matches. And if they do not match, it may not use it, or it may actually refresh the cache with the stuff from disk. You can specify with the shared cache to make it read-only and therefore no updates. So what you may want to do is run most of the time with, say, read-only mode, and then occasionally, like once a week, run without the read-only and update all the shared classes. That's an area I'm not familiar with. And it can also do garbage collection on things which are superseded. But that's an area I'm not that familiar with. So if the Java shared cache class is so wonderful, why does no one talk about it? I think perhaps on sort of the people who develop the code tend to run on real boxes. And for them, Java starting up in 5 seconds compared to 10 seconds gives them no benefit. Whereas for me, starting up in, I think it's 170 seconds compared to over 400, it's a big deal for me. So it may be that people who sort of control these things actually have the real hardware to run on and therefore think it's not important. I also think that many people do not understand it, and that, for example, they turn it on and say, well, the first time we use it, it made no difference, so we'd turn it off again. But as I showed you in my charts, it takes the second restart or a second JVM to benefit from it. I also, reading some of the forums, someone would enable it, but they did not save it. So next time they IPO'd, they had to start from scratch again and say, well, we've got no benefit here. It's not helping us. I also saw one comment where they would actually save the default directory /tmp, and every time they IPL the box, the procedures were to clear /tmp. Therefore, any saved files got deleted. So I think there are many reasons why it's not done, but I think it would be great if all products could ship with the shaved image already jittered, so it actually comes souped up, ready to go really fast. But that's my personal view. This one, the first one here is making it go even faster. I did have a play with tweaking some of the JIT options. You can say, if you say to JIT, optimize the code whenever it's being used, you can say count equals 0, it says. So even if the count is greater than 0, start optimizing it. Well, the first time I did this, it was very slow. The second time it was faster, but I'm not sure if it actually works for everybody, because someone did say if you JIT everything, it may actually go slower. So that's the first one, is what I played with. It may make no difference or make it go worse. The second one was an interesting one. When I started the Zoe system up, it starts up 3 or 4 JVMs, and the all by 5 engine suddenly became 100%. The fans came on, the lights dimmed, and so on. I think a lot of that was because there was so much work being put onto the JIT threads that there was no time for any other work. So you can actually specify compilation threads, in my case 3, which says only run with 3 threads. And now everything seems to start faster, but it might take longer to get all the code JITted. So it might be worth playing with this option yourself to see if it's the impact on your system. If there's a big impact when you start Java, tweak this down and see if it helps. You can do traces. For example, if you just turn on the option trace with verbose, it says I'm loading these various classes. The JRT basically says this is the boot Java Bootstrap code, and it's got some stuff in it. It's got Java bases, it's got maths, iterators, arrays, etc. But at the bottom, we can see there's a Spring framework. The Spring framework is a way of writing complex Java programs quite easily. It does lots of work for you. And we can see this class came from a file called /u/tmp/bin gateway. We can see which jar it came from. If you put it on the verbose IO, it gives you more information. For example, I can see from the top couple of entries at the start of this thing, there was a class loader, and the class loader is number 0, and it loads it. It also says it failed to find a program in the shared cache, but then went on to load it anyway. So in looking into that, you can get more information. For example, I found that the Spring framework has its own class loader, and it's doing clever things. So we can see entries like class loader 0, class loader 2. Now, the Spring framework, quote, optimize the code. Instead of having a jar file full of classes, they have a jar file full of jar files, which can have jar files within it. And the shared classes cache does not support the nested classes yet. I raised a defect with the Java development team, and they're looking at a fix which may come out in the third quarter. But for running Zoe, 80% of the code cannot go into the shared cache. I took a build and did my own build, turning off this clever support from the Spring framework, and that's where I got the huge benefit from down from about 400 seconds down to about 170. So hopefully, when the fix comes out in Java, Zoe support for everybody should go much faster if you enable this support. All right, any questions on the Java shared classes from anybody?
I have a question, mostly just a comment, I suppose. So, we're working at deploying WebSphere Liberty under Kix into production at the moment. So we've been looking at using shared class caches for that. I think probably our main objective was that we'd get, increased performance if we have several JVMs, which we do on each LPAR, and also maybe reducing the memory use, even though I don't know how important that really is these days. But interestingly enough, one of the guys at IBM recommended that we have one shared class cache for each JVM, which isn't really shared then anymore. Because
So when you say per JVM, do you mean per Kix region or per JVM?
yes, per Kix region, per JVM instance, I suppose, if you will. Um, but we only have one JVM in each Kix region. I mean, you could have several JVMs in each Kix region, but we don't do that. But he made the point that it's got reliability issues sometimes because you don't really get warned if the shared class cache is getting full. And if it does become full, you have to bring down your JVM to empty it and probably increase the size of it. So just I suppose in terms of, you have had a slide on the reasons for it not being more popular than it is, that it does seem that the recommendations vary quite a bit as well on how to use it. I think personally, I mean, we've not made a final decision on this yet, but I think it seems a bit, I mean, the benefit seems very limited if we're going to have one shared class cache per Kix region. They would be quicker at recycling, but having a performance benefit sort of while they're up would would be good as well.
Do you save the cache across IPLs?
I don't think we do at the moment, and also IPLs are really rare in production, so it's not been
So
a
it sounds like you're not actually exploiting the shared cache because it only happens from the second. In the picture I had where I restored the cache, then the next time you start your JVM, that's when you benefit. It feels like you're starting cold every time and not benefiting from the stuff for the performance side of it.
yeah. I mean, I suppose to us the main benefit seemed to be that if one Kix region did, compiled a certain class, then that compiled code would be available to other Kix regions on the same LPAR.
Yes, um, I would also think some customers, for example, will roll an application out across different Kixes and you put it onto this subset of Kixes first of all, then the second, then the third lot. If you were to share your um, cache across those systems, you might be picking up the newer version of the code, which you might not want. You
Mm.
might want to, if you were to share it, you have the cache shared by the first group and the second cache for the second group and so on.
Yeah, that's a good point. Yeah.
The person in a guy called Phil Wakelin,
Yes.
he's the one who knows all about this. I've been speaking a lot to him about it.
There's
So
Phil,
what he says, he's the expert on it.
exactly. Yeah, and it was him who said that maybe we should consider just having one shared class cache for each Kix region.
as
Uh,
long as you restore it. And so in that case, for example, you'd have as your name, where I had Zoe GW as my name, you'd have it like name equals kicks1.
yes,
And
that is what we've done for testing that. I suppose it's just yeah. I think we do get a startup benefit as well because we recycle our kicks regions much more frequently than we do IPLs. So even if they're not persistent across IPLs, they would be persistent across kicks recycles.
yes, absolutely, yes.
But yeah, it's still something we're testing. So I was quite keen on this presentation to learn a bit more about it. And I did just put a question in the chat as well. I was wondering, because you showed before, you said that you'd found that 80% of the classes you had for Zoe weren't actually eligible. How did you measure that? Because we use Spring Boot, so I was just wondering how I could find that sort of information for.
I use the verbose IO trace.
Right, and
And
then
it says basically couldn't find it class loaded 0, couldn't find it class loaded 2, read it from disk. So I thought, it can't be found by a class loader, or why not? And it's because the name is sort of /a.jar exclamation mark / abc.jar exclamation mark / dot. So it was a nested jar, and I think the problem is that it doesn't like the name of that jar, it doesn't like the nested jar for some reason.
okay. No, that,
Um, Going back to one thing you made, some customers said they like the IPLs to be fast, especially after a disaster outage. So they want to get up as quickly as possible. So by having your shared classes cache restored at IPL means your first kicks comes up at that bit quicker. Whereas that bit quicker might be 2 seconds. I don't know.
no, that makes sense. And I suppose if you use that, if you use a persistent option, you don't need the snapshots anymore.
I test it out. I don't think persistence works. I'm
Right.
saying when you shut down kicks, the last step is you save snapshot the cache.
Right. Yeah, I get you.
And IPL, you say restore cache. So when you start your kicks, the cache is already restored. It might save you 10 seconds of startup time, or however long it takes to on your system. This is small details. These are like sort of 0.1% improvement type things.
No, that's useful to know, though. Thank you.
Any more questions? Right. Okay. How much more time do we have? It goes on till 12 o'clock, isn't it? I think.
Yeah, till 12 o'clock. So
Okay. So I'll whip through some of these performance things quite quickly and might skip over some boring things. My I spent about 10 to 15 years in the area of performance. So I've covered things from MQ performance down to application stuff. So there's lots of different topics here. And I've tried to allow for people of varying skill levels. A question I was asked was, why do we have XP Link? And if you think about some applications in C and Java, you call a function and the function does nothing like, say, set value equals 6. So you've actually a 12 instruction call path length to actually get there. It does 2 instructions and returns. Now, they used XP-Link, and basically they can pass parameters in registers rather than storage. And so it might only take 3 instructions to get into the function and 2 to get out again. And I think that when Java was changed to use XP-Link, they basically doubled throughput overnight, I think. So the XP-Link does go faster. You have to change your program to compile some options, but otherwise it works pretty well, and it's the way to go for some things. I run ZOS on my laptop. So I think it's quite neat that I can run Java on ZOS, which I think runs on an emulator written in Java on an 886 box. And somewhere there's a piece of Java which says, this is a load instruction. I would jump to the load Java code. If you were to put a Z17 box into a scanning electron microscope, there would be no wiring for the load instruction. It's all microcode. So just as Java has interpreted bytecodes, ZOS has actually interpreted bytecodes, which I thought was quite an amazing concept when someone told me this. As the microcode does all the hard work. Digging down into some instructions. In the early days of the first CPUs, there was one task which did all the work. So it would take your instruction and say, oh, this is a load, I will do all the work. Now, these days, it's a whole factory, it's a whole production line of different steps to actually execute the code. For example, the first thing it does actually the parse instruction is, this is a load, and there's a register 4, a register 6, and an offset of 8. And it then goes away and locks register 4 and register 6 to make sure other stages in the pipeline of the production line can't actually change it. It calculates 8 of register 6 and calculates the real address of the page. Now, this can be quite a long calculation because you might be like 4 or 5 levels of virtualization deep. And each one of those, the real address is actually not real, it's a virtualized address. It can also take a long time to go and get the storage. For example, the storage you're after could be on the same CPU where you're running. It could be on the same chip, which is a piece of silicon 2 inches square. It could be in a different chip in the same book, or it could be around the corner in a different book, and that could be perhaps a meter away. So the time taken to access the storage could be less than a millimeter or up to a meter in distance. So the storage access time can be very long. So when it's got the storage, you say execute, and it still moves the contents to register 4 and releases the lock. That is a very simple picture of modern day technology. So what happens if I now have a real program? So I now, for example, have the same instruction at the top, and I now say, okay, having loaded the register 4, I copy that into a different register, subtract some registers, and do another load register. When the first load register comes to execute, it says lock register 4. Oh, it's locked. I actually cannot get the data. So this now has to wait until the first instruction is finished. So it'll wait. You can actually rearrange this code to do such things as move the subtract register and the other load register above that. So by the time these two are finished, the actual load register using register 4 may have finished. So just by reorganizing the code, you can make it go faster. Now, I remember the CICS development team was responsible for the dispatcher back in, this is about 35 years ago. They were so pleased that they could optimize the code by rearranging the instructions. They got like a 1% performance benefit. But then they got a new box, next generation hardware, and found all their careful tuning just didn't work. And they found that letting the compiler and specify we're on this little box, the compiler could generate better code than they could. So these days, rearranging instructions doesn't actually help that much. Letting the compiler do it because it knows how long the pipeline is and things like that is much more efficient. And I believe the hardware itself can actually rearrange these instructions, but as long as it does the commits in the right order, it doesn't matter. So the hardware, I think, is very clever and actually does this optimization for you. Another thing is when I first took over the performance reins, someone said, compile your code on the latest compiler. Such things as the load register 4 from the value of 4 requires a storage access. But if you use the load register load immediate, the value is actually the instruction, so it's actually much faster. Okay, I'll skip over a couple of those quite quickly. This is a war story. I was at a customer and they were having terrible performance problems. And this is some of this example of DB2. I looked in the DB2 stats and can find that these values were cached. If they've rewritten it like this as a one, get the rest of it coming up, it could parse it and keep a cached copy in memory. With the top two, because every statement was different, because it's got a different user ID in it, it had to go through, parse the statements, go and do a security check, do all the DB2 checks. With the second statement, it did it once, and the CPU dropped, I think, by a factor of 25% overnight just by making this change. It's also interesting that the top code, this is 2 weeks and going live on the application, printf was the highest function because they had all the debug code in it. Don't do unnecessary work. There's a customer had an application, which is a very, very advanced application, which says, whenever you go into this program, check this flag. If it says, say, the value of 57, do it the new way. If it's less than 57, do it the old way. This allows them to disable new function very quickly and not, for example, have to restart CICS or load all the programs and things like that. But the CICS performance person said, you're doing this 1,000 times in your program. Of course, they didn't believe him, but eventually they found it and said, okay, it'd be much easier if you have a flag, do it once if you want to, but don't do it in every application. In the end, they actually did it once at Kickstarter and stored in the GWA. So don't do unnecessary work. Okay, let's moving on a bit. Oops, get some interesting things. I found this interesting. Multiplication is expensive, relatively expensive. So if, for example, you want to multiply by 10, it's much quicker to take the value, shift it left 3 bits, and add to it, shifted it left 1 bit. Because on the chips these days, there's lots of different processes that can do shifts very quickly. So in that case, doing a multiply that way uses 2 clock ticks. 1 clock tick to do all the shift lefts and 1 to add them. Divide is very expensive. And for lots of the processing, for example, where you're doing some of the AI stuff and you're doing millions of calculations, they can actually get away without doing any divide. So if you look at the value 1024 over 3 is 341. So if you multiply by 341 and divide by 1024, this is the same as multiplying by 341 and shifting it down 10 bits. So actually, you're not doing a divide, you're doing a multiply and shift. And you can actually do the same, instead of doing the multiply, you can again do the same shift calculations as you do on the top. And apparently, if you do it this way, it's much faster than doing multiplies. And using the compiler, it actually optimized the bottom calculation to do the shifts rather than actually the divide itself. Okay, let's skip that. Let's skip that and skip that. Get to an interesting one. Okay, as a getting towards the end, this is what I think a very interesting area. It involves in MQ. We have it's the same code in such things as DB2 and other products that have one trace table across multiple TCBs. So what we did, we'd load the register 3 with the current trace pointer and save it. We'd point to the next one. Then we do a compare and swap to update the trace pointer. If it's successful, we have a pointer to our trace buffer. If it's unsuccessful, you go around the loop again. Now, I was told when I studied performance that load register is very cheap and a compare and swap is very expensive. So on this, a quick question for you, which is the most expensive instruction in duration? If it's single threading, the compare and swap is because it had to do 2 storage updates. But if you're doing multiple TCBs, the first instruction, which is the load with the current trace pointer, had a lot of storage contention. Sometimes the pointer was in this chip's memory, sometimes in the same book, sometimes it was around the corner. So most of the time was actually spent in this top instruction. And the compare and swap was really fast because the data was actually in the same chip, in the same CPU as the instruction. So we actually solved this by giving each thread its own buffer and merged it at formatting time. And that's basically a hotspot just disappeared overnight just by making this fairly simple change. Right, and that should be the end of my session. And it's 45 minutes. Any more questions? Stunned silence. Good.
Oh, is there a question there? No,
Ooh.
just thank you. Yes, that was a really interesting session, Colin. Thank you so much for coming and presenting for us and supporting us like you do. And thanks to all the attendees. Please don't forget to do the feedback because it's really important to us and to the speaker. I think that we now have a break for half an hour and there should be another session in this stream. I won't be chairing, so it will be either Martin or Nathan. So enjoy the rest of the conference. Thank you.
Thanks, everybody. Bye-bye.